Hello Year 11s, this is the Half-Life exam marking. Make sure you have your green and your blue pens ready. So starting with question 1, some of the rocks inside Earth contain the radioactive element uranium-238, and this graph shows how the count rate changes with time. Now all the Half-Life graphs or count rate graphs will always decrease over with time, so they will always show this curve decreasing. The question says here, the graph can be used to find the half-life of uranium, and the half-life is 4,500 million years or 4.5 billion years. And just to double check, half-life, the definition is the time taken for count rate or activity to halve. So we have to draw on the graph to show how this can be used to find the half-life of uranium. So you'll need your ruler. Finding 4.5 or 4,500 in between here, and we hit the curve, we read across, and if the question did ask us about the counts, it would be 500 seconds, but here you just have to show it. Moving on, next question. There is half as much uranium in the rocks as there were when Earth was formed. How old is Earth? So let's say Big Bang happened and we started off with, just for ease, 10 in terms of the radioactivity, and we're looking at how long how long it has been until, let's say, now, where it has become now 5 for our activity. And very simply, when you look at it like this, you can see that the half-life will equal the age of the Earth. So it's told us before that the age of the Earth is 4,500 million years, and therefore that is what we pick. Or we could say 4.5 billion years as well. So if a sample was available, why is it not possible to measure the half-life in a school experiment? So you're explaining why. Well, very simply, the half-life is way too long. I don't think any of us will be around for millions of years. And also, there is just no measurable change. Because it's so long, the change is so small, we can't really measure it. Now to a half-life calculation. Americium 264 can be used in smoke detectors. We have a proton number and a mass number, and we have the half-life, which is 433 years. It says how long would it take for it to decrease by 1/8 of its original number. So if we were to think about how many half-lives it would be for 1/8, from 1 to a half, you have 1 half-life. A half to a quarter is another half-life. And to an 1/8 is 3 half-lives. And so if my half-life is 430 years, and that's 1, 2, and 3, well then, total up, times by 3, the total original number that was 1,299 years, and that is my answer, 1,299 years. Okay, moving on. We have a radioactive source that emits alpha, beta, and gamma radiation, and underlining these, let's go for the charges. Well, alpha is positive, it's positive 2. Beta is negative, it's negative 1. And gamma does not have a charge, it's an EM wave. This diagram shows what happens to the radiation as it passes 2 charged metal plates. Now the top plate here is negative, and the bottom plate here is positive. Now let's see, particle P is attracted, because as it moves, it bends towards the negatively charged plate. Therefore, we know P is going to be a positive particle, and we know P is the alpha particle. Q passes straight through, it's not attracted, therefore with no charge it will be gamma. And lastly, R, because it's attracted to a positive plate, and as you know, opposite charges attract, R will be beta. So which line, P, Q or R, is the path taken by alpha radiation? Well, it's P, and gamma radiation, Q. The graph shows how count rates from 3 different radioactive sources, J, K and L, change with time. And you can see here, they all change with time. How? They are all decreasing with time. Which source has the highest count rate after 24 hours? So even if we look at 25, here, the source with the most will be K. How about for source L? What is the count rate after 5 hours? So here's L. Let's find 5. We draw a line up to hit the curve, and we draw a line across to here. Now it's the troublesome part is reading to scale the scales. So here there are 5 squares, and it goes from 0 to 20. So 20 divided by 5 is 4. That means every single square is worth 4. So we have 40 here, and there are 1, 2, 3, 4. So 4 times 4 is 16. Add 40 is 56. So therefore, our count life after 5 hours is 56. And lastly, which source has the longest half-life? Well, you're looking for the one that's going to take the longest to hit 0. So which one is going to get to 0, take the longest to get to 0? And it will be K. So if we extend it down, it will just take forever to meet 0. So it is K. Next, doctors may use nuclear radiation to diagnose certain types of illnesses, and the table of 3 different radiation sources are used. Each source emits beta radiation. So we have carbon, nitrogen and oxygen here, and this is the half-life in minutes. Now bearing in mind, we do not want to have exposure to radiation for a very long time. Okay, so next question says, we are explaining why oxygen is likely to produce the least risk. Well, let's see. Oxygen has the lowest half-life, so the shortest half-life, and therefore we will have the exposure time to radiation is shorter. Next, we are plotting. So here we have a table for count rate and how it changes over 10 days. You are asked to draw a graph of the count rate against time and include a line of best fit. Now, one thing to note is in science there are 2 types of lines of best fit. You can get a straight line, or you can have a line of best fit which is curved. And you should see, you should try and plot them up, join them up as a straight line using a ruler, or curve using a free hand. And if you look at the half-life, the count rate versus time graphs already, you can see they're all curved. So you are actually expecting a curved graph. So I have already plotted my points, but remember we're doing crosses for plots. And to double check the scaling, there are 5 lines here, and 100 divided by 5 equals 20. That means every line is worth 20. And that's how we are plotting there. The only one which might be more troublesome to plot is, for example, 90. So we find 80, and then it's halfway in between there. So we are using our graph to find, oh, haven't finished this question yet, we need to draw our curve. So as I said, we can't use a ruler because it curves, and you have to kind of use your hand like a compass, like the arm, the elbow in your arm like a compass. So we start at the top, and we're drawing in one smooth movement the curve through all the points like that. And there's our curve there. And we're using our graph to find how long it takes for the count rate to fall from 880 to 440 counts per minute. So we find 440, so 400, 420, 440, which is there. And we read down, and we can see it's about 3 days. And what's the half-life of a substance? Well, remember, half-life is the amount of time it takes for count rate activity to half, and here it's halved, so it's the same. It's also 3 days. Okay, next question we have here is that the table gives a half-life of radiation by 4 different radioactive isotopes. Which sample will have the lowest count rate 1 month from today? Well, the one with the lowest count rate will have the shorter half-life. So if we look at our table, the one with the shortest half-life is radon 222. Oh, and give a reason for your answer. Well, we have said it has the shorter half-life, so shortest half-life. Another calculation we have here is tritium is radioactive. After 35 years, we have 10 grams of tritium remaining from the original sample of 80. So this is our initial here, and 10 grams is our final, and that's after 36 years. We are calculating the half-life. So if our initial is 80, after 1 half-life it will be 40 grams. Not the same yet. So after 2 half-lives, 20 grams. Still not the same to our final. After 3 half-lives, we keep going. Oh, yep, it's our final one. So there we have 3 half-lives. That means that in 3 half-lives, that is in 36 years. Instead, I want it with 1 half-life, so I have to divide by 3. And this side, if I divide by 3, my final answer, 12 years. Final question we have here. Plants absorb carbon-14 from the atmosphere. And here is the decay curve here. Again, it's a curve because count rate will decrease of a flax plant. And use your graph to find the half-life of carbon-14. You should show clearly on your graph how you obtained that answer. So let's check then now. We have, checking our scaling, every single one, so every 2 squares is worth 1. Okay, and we check our scale to the top. This is 16, roughly about 16 where it starts. Half of 16 is 8, so 6, 7, 8. We draw a line across, a horizontal line across, and our line downwards to there, roughly about there. Now we need to know the scaling at the bottom. Every 2 squares is worth 1,000, so this one here is 6,000. In between the 2 will be 5,500 years. Now this last question is a very challenging question. So linen cloth is made from a flax plant, and in an exhibition they say that it might have belonged to Saint Thomas a Becket, who died in 1162. So Thomas a Becket, Thomas Becket. Extracting carbon-14 from the cloth will allow the age of the shirt to be verified. If 1 gram of carbon-14 is extracted from the cloth, or to give 870 counts an hour, would it be possible for the shirt to once belong to Thomas a Becket? Now the first thing, and showing your steps. The first thing we are looking at here is that it produces 870 counts an hour. But in our graph, it's count per minute. So we need to make sure this is in minutes. So to make sure we're using minutes, we're dividing by 60, and 870 divided by 60 is 14.5. We look at our graph to find 14.5. So there's 14, and 14.5 is just there. And if we look down, and we draw a line downwards, and then the scale, I understand, is very, very small here. It's in between 500 and 1,000. So the count rate will be, the count for 14.5 counts per minute ends up being 750 years. Now, if we look at our current years, if we minus our current year, 2019, take away when he should have died. That means there's a difference of 857 years. And this means that more time has passed. The count rate should be lower. So could it belong to Thomas à Becket? Well, no, it couldn't.